Ram Sriharsha, VP of Engineering and Research and Development at Pinecone. Welcome to the Data Exchange Podcast.
Thanks for having me, Ben. It's great to be here.
So I have known, for our listeners, I've known Ram for many years, since the early days of Spark, actually. So in fact, I always think of Ram as the person who basically shepherded Spark SQL when it was still called Shark, because he was at Yahoo and he was kind of like a champion of Shark or Spark SQL at the time inside Yahoo. And honestly, now in retrospect, that was at the time when Shark was really quite early and maybe not not quite yet ready for prime time, honestly, right? So, but anyway, so then. We've known each other for many years. So I was kind of interested when I noticed he moved to Pinecone, which is one of these leaders in this new category called vector databases. So this episode is a deep dive into vector databases. So with that said, Ram, I guess I went to your website. I looked at kind of this post, what is a vector database? So let me read you back what you guys wrote. Vector databases are purpose-built to handle the unique structure of vector embeddings. So is that still an accurate description?
Yes.
And so then generally, where do these vector embeddings come from? So our listeners might be familiar with these language embeddings, right? So Word2Vec and others. So what are other examples of vector embeddings?
Yeah. So vector embeddings come from everywhere. So first of all, taking a step back, vectors are the best way we know of to deal with unstructured data. So if you have unstructured data and complex questions like, is this document similar to something else? Is this image nearly a duplicate of something else, and so on? A few years back, we couldn't even ask and answer these questions. These days we can, because deep learning technology and modern machine learning has gotten very far in allowing us to answer these questions. So to answer your question, vectors can be generated from anywhere. For example, images, you can pass them through a model like ImageNet or some fine-tuned deep neural network and get vectors. These are fixed dimensional array of floats, if you want to think of it that way. You can also get vectors from text, right? BERT transformers do that. A lot of modern.
What about audio?
Audio, video, even time series data. Even there's like user preferences can be a vector. There's just plenty of ways to generate these vector embeddings. Some of them can be sparse embeddings, some of them can be dense embeddings, but in general, vector embeddings can come from anywhere.
So, for example, in the area of text and NLP, which I'm most familiar with, there are tons of embeddings to choose from.
Yes.
So much so that you actually need guidance, right? So depending on your use case and your problem, right? So there's sentence embeddings, there's BERT, there's Roberta, all sorts of things. So once you have the embeddings, so why store them? So what's the key use case for having a database? So database, the most basic thing is you store it, right?
Yes. Yeah, that's a great question. Probably the simplest use case I can give is, imagine that you're trying to do image deduplication, right? So you have a huge corpus of images and you want to detect whether something is like a near duplicate, right? You cannot do this without storing. For example, every image that you get, you would have to convert them into some vector. You would have to store them somewhere. And you need some scalable way when you get a new image and a new vector to say, how close is this vector to whatever is in your corpus? And if it's closer than a certain threshold, you can say that that's probably a near duplicate, right? That's a very simple question that you want to ask and answer, for which you A, need a way to convert things into vectors, and B, need an extremely scalable way to search the corpus of vectors and identify something that's nearly a duplicate.
And C, you need a way to be able to formulate the question. So in structured data, you have SQL, right?
Yes. Yes, the most important thing is we already, while I was kind of being ad hoc here, I already precisely formulated the question, right? Because I converted the question of detecting near duplicates into create these embeddings and then do nearest neighbor search over these embeddings and then use a threshold to detect whether something is a near duplicate. Suddenly I've taken a very unstructured question on a very unstructured set of data and given you a very precise way to answer it, as well as a precise way of structuring the data. This is what I meant at the beginning by saying that modern machine learning has taken us this far. We can actually start thinking about these sort of problems in a very structured way today.
So Ram, when people hear the word database, they usually think of relational databases. So let's go through some of the kind of the basic features of relational database and tell me if these map over to vector databases, right? So you have, I guess, indexes, right? So I think there's indexes in the vector databases too. Vector database too. So what else? So do you have the notion of transactions and things like this?
That's a great question. So again, even in databases, some databases have certain notions of transactions, some have others, right? Some databases are eventually consistent, some databases have strong consistency, and so on. So there are notions of consistency, there are notions of transactionality. Databases always involve data management, right? Somebody has to be able to observe data, delete data. Your indexes have to respond to that.
And then when you get into bake-offs, you have those three things that people use to compare: latency, concurrency, throughput, right?
Yes, and we have all of them, right? And fundamentally, we have all the data management problems that you would have in a typical database. The only difference is we are serving a very novel use case, which is search, right? Searching these vector.
So search is basically the main rationale.
Yes. Yeah. This sort of searching across vector embeddings is the primary use case, but it forces a design of a database that's so different from relational databases in the traditional design that it deserves its own category. That's really it. It's all the data management challenges applied to an entirely new use case and an entirely new data type, which is vectors.
So let's say I invite you to give a keynote at a conference. I give you 3 to 4 slides of the most impressive case studies and use cases for vector databases. Set aside Pinecone, look broader into the vector database category. What would those 4 examples be?
Well, the most important use case for you're asking mainly use case of a vector search, right? The most important use cases of a vector search are in recommendations. So product recommendation, retail recommendations, like probably the number one use case. That's kind of how this technology came to be, which is to target those sort of use cases. But then over time, there have been other use cases that are equally important, or if not more. The second use case I would give is semantic text search, right? So if you're doing semantic search over text, this is trying to find things by meaning, right? For example, by the way, this happens even today. So if you go to Google and type something like, I'm looking for canned soda.
Because now they use embeddings, right?
Yeah, and you may get an ad for a Pepsi or a Coke, or you may get hyperlinks for those sort of things, where canned and soda may not actually be in the content, right? But clearly, it's clear to us that canned soda and Pepsi are kind of the same semantically related things. This is only possible with technologies like vector search, right? Traditional keyword search simply cannot retrieve those sort of documents for you. So people have already been doing this. The Amazons, the Googles, the Microsofts of the world have already been doing this. We are just democratizing this technology and scaling it and making it a SaaS product and solving all the data management challenges as well. So semantic text search is a great example. Product recommendations, retail recommendations is a great example. More sophisticated examples are around security analytics, right? In security analytics, you're kind of doing a little bit of the opposite, which is you're not looking for very similar events or very similar things. You're actually looking for something that's very dissimilar, or anomaly detection, right? You're trying to look for something very
So
anomalous.
what is the raw material there? Is it time series or logs?
Logs. It's logs. It could be time series. It could be user activity, right?
Okay.
Or system activity, right? And in general, enterprise search, whatever you would think of as people do in enterprise search, almost invariably we are seeing use cases around that where people can either do it better with vector search today, or vector search complements their existing technologies and identifies new things that they would have missed.
So let me ask you about the recommendation example. So in the recommendation example, are you saying, let's say I'm clicking on a book on Amazon, and you use the embeddings for that book to find similar books? So
yes.
it's straight up similarity to the book I'm reading.
Yeah,
it's not a recommendation based on some machine learning algorithm.
So yes, yes and no. The machine learning algorithms may produce the embeddings, right? So there are machine learning algorithms that
but the embeddings are already stored in advance, right?
Exactly. After that, it's a straightforward similarity search, right? Now that similarity search could be done with something as simple as inner product similarity. So inner product between user and rating, for example, or inner product between item and item. It could also be done by models. You can actually have models that determine what is similar to what. So both can exist.
So what is the relationship between vector databases and two other kind of emergent categories? The first one is graph database, which is slightly older. And then the second one is feature stores.
It's a great question. Vector databases and graph databases, I would say, are very, very different from each other. So you can think of graph databases are kind of like SQL databases, right? The only difference is that instead of dealing with relational tables, you're dealing with graphs and edges and vertices.
Right.
So that's it, right? So basically, it's a very efficient way to express graph structure and to query things that are dependent on.
But there's the reason I bring them up is they also encode some notion of closeness and similarity.
No, so
but in a different way, in a kind of a relationship kind
exactly,
of way. Right.
Exactly. The only similarity that they encode is predetermined relationship, right? So you predetermine that there's a relationship between two quantities, and you express it as a link or a edge, and then you can ask, given two other quantities, is there like a indirect link between them? Meaning, can I go through these relationships and get to that other? That's all you can do. Whereas with approximate search and like vector search and so on, these are not pre-encoded relationships, right? What is similar is really determined at query time. Does that make sense?
Correct. Right. So what about feature stores?
Yeah. So curiously enough, we have seen some customers of ours use Pinecone as a feature store, meaning just because we are so fast at storing and retrieving vectors, you can use us just to store and retrieve vectors. But that's not our primary goal. Our primary goal is to provide a very efficient search over vectors. So, right. So feature stores basically are for storing and managing and retrieving vectors. That's it. So the operations you care about are just putting a vector into a feature store, getting that vector back, using it in some pipeline or some workflow from there on. It's not a database that's purpose-built for search or any of those things.
So vector databases kind of are really only possible now because of embeddings and machine learning, right? So if you look back 5 years ago, this category it wouldn't exist.
Exactly. Yeah, it wouldn't exist because the machine learning techniques weren't prevalent and rampant up until now. We didn't have very high quality models. For example, the sort of models you get from OpenAI, from Hugging Face, and from all of these models that people can just use and start putting together semantic search workflows very easily. It wasn't possible like 5 years back, right? And the technology to even do scalable vector search, while it's still a research problem, it's far more mature than it was 5-7 years ago.
So, Ram, since everything is a vector, in many ways, and I don't know if this is the case, are vector databases canonically multimodal? Meaning I can store vector embeddings of text, audio, video, images, all in the same thing?
You can. So most vector databases today, and actually practically all of them, essentially fix the dimensionality of vectors. So as long as you can convert all of these into like a fixed dimensional vector, you can store them. People can use it for multimodal learning, for multimodal search, and so on. It's doable. It is there is research work that shows how to do it, and yeah, you can technically do it. Though people don't tend to do that today, as far as I can tell. I haven't seen a use case like that yet.
So in practice, what's the workflow then? Let's say I'm interested in semantic search, right? So I have a bunch of documents, legal documents, whatever, healthcare documents. So do I first say, okay, so these are my documents and this is the embedding I want to use. So I have to prefix the embedding?
You have to know what the embedding model is. So you pick an embedding model, right? And you would pass your documents through the embedding model. You will either tokenize them, convert them into sentences, for example. Then for each sentence, you may have an embedding. Then you send those embeddings to Pinecone. Then you have a query. You again have a query model. And then you have to pass your query text.
But what about if 2 weeks later I decide, this embedding is great, but I want to try the sentence embedding?
Yes. So this is a great question. One of the reasons why we have this concept of we just recently released this concept of collections, which is it allows you to take your data and send it to Pinecone first, and then you can run things on top of them and re-ingest stuff and so on if you wanted. Generally, today we consider this client-side problem, which is you have to have your embedding models and you have to have a workflow that actually sends vector embeddings to us. If you do have to,
I'm responsible for doing the embeddings.
Exactly. So that's a client side problem today. Now we are investigating a lot of ways we can help people here, but as of today, I would say it's a client side problem. So which is embeddings are generated by customers, sent to us. We aren't strictly a vector database in the sense that vectors are not the only thing we accept. We also accept something called metadata, which is basically like a JSON that describes something about the vector. And this is very useful when you want to filter and you want to restrict your space of search to things that match the metadata.
So let's see. So if I'm doing things at scale, let's say I have, I don't know, 1 billion documents.
Yes.
And then I have to do these embeddings and send them to Pinecone.
Yeah.
So first of all, I need to find a scale out way to do the embeddings using Ray or something, right?
Yeah, and there are also OpenAI.
Because I can tell you embeddings, if you try to do them, if you try to do a lot of them on your laptop, it can get slow.
Yeah, you shouldn't. We typically advise people to use services like OpenAI, Hugging Face, and all that. There's a lot of these services coming up today, which with one API call you can actually create embeddings.
Right, but like I said, what if you have a lot of documents and data, right?
Yeah.
So then what about the JSON metadata file that you described? So so for each document or each image, I have to supply that to you as well.
You could do that. An example would be imagine that going back to the product recommendation setting. Imagine that you're sending us vectors. You could also send us metadata like the price of the item or like the region it's available and so on. And then during search, maybe you're only interested in surfacing the most similar product if it's available in that particular region. So you will then prefix your query with like a filter that says, oh, by the way, consider only the most semantically relevant content subject to this condition, right? Which, by the way, turns out to be a very hard problem to solve from a database point of view.
So in terms of indexing, indexes are fundamental, right? So in order for it to be fast and performant. So is that something that users have to do themselves, or is that the system automatically does the most optimal way of indexing?
That's a great question. So one of the core principles of Pinecone is to have the users do as little as needed In fact, we don't really expose index tuning parameters and so on. If you look at a lot of algorithms out there, there's a lot of things you have to tune to actually get them to work well on a particular data set or a particular workload. We tend to build algorithms that work really well on a variety of workloads. So they have strong worst case bounds. So indexing is done by us, managed by us, and no tuning is expected of the user.
So the typical the typical person who uses Pinecone is who? Are they platform engineers, or it doesn't seem like something that data scientists would necessarily use, right? So
that's a great question. It's either ML engineers or production engineers and so on. Yeah,
right.
Platform engineers, ML engineers, production engineers.
Because it shows up mostly in search and recommendation, right?
Like I said, many use cases: search and recommendation, semantic search, and so on. Data scientists are often, we find data scientists are often involved in evaluating the platform, in making sure that the use cases that they're trying to productionize can be thought of as like a semantic search or like a similarity search use case. But the actual integration that people often do, it's usually ML engineers or production engineers who are integrating with Pinecone.
So these vector embeddings compress data, right? So in other words, if I have an image, I do the embedding is smaller than the image, right?
Yes.
So then do these vector databases need to be distributed? So in other words, they're so big that you need to scale out?
That's a great question. So first of all, vector embeddings both compress your raw data, but also in a sense extract the key component of the data for representation purposes, meaning to detect similarity between two things, it's enough to look at the embeddings, which means that embeddings have to have enough content in them that they capture the essence of that similarity problem, but they also compress the data.
So let me press you on that. So how do I, as a user, know upfront that I've chosen the right embedding? Right. So maybe I need to kind of try a bunch of embeddings on a small sample of data, right?
Yes, you do. And often what people do is people even take things like BERT transformers that have been built on general purpose corpus. What is surprising and very effective is even the general purpose transformers usually do pretty well on a lot of semantic search tasks. But you can also train a smaller model on top of it. It's called fine tuning, that on a small sample of your data, you can actually make that model better. For that, you need samples, you need some training process and so on.
But again, the user is responsible for that, right? So so the vector database only starts when you already have the embeddings.
Yes. Yes, today. Yes.
Yeah. So then, I guess I'm kind of hung up, Ram, on this whole, how do I know I chose the right embedding?
Yeah, I think so. Today, a lot of the work has to be done by the customer, the user.
Yeah.
There is a lot of material out there. There's a lot. In fact, Pinecone publishes a lot of material on how to do this well. There's a lot of
but there's a certain trial and error involved, right? So
100%, which is definitely true. There are areas where we are really thinking about here how to reduce that gap. But trial and error is involved today. Where Pinecone fits in today, or where vector databases in general fit in today, is once you have good embeddings and you're trying to now solve this problem at scale and actually trying to productionize this, that's when the vector database comes in. And to go back to your question of distributed, even though the vectors compress the original data, you're still talking about a lot of data, right? A typical vector for us is 768 dimensional. When it comes to text, it could be even 2000 dimensional, 2048 dimensional when it comes to images and so on. That's already 4 kilobytes or 16 kilobytes and so on. That's a lot of data, right? Just for a single record. And then vector search is very, very computationally intensive. It's probably the most computationally intensive part of any database that's been built, which means even scaling that requires often sharding, often using a lot of CPUs and so on.
So is there like because I have a bunch of vectors, right? So when you scale out, do you have smart strategies around partitioning and placement?
That's a great question. in some sense, it depends on freshness as well. So for example, if you really want to respond to an update extremely quickly, that limits the strategies that you can employ. For example, you can just, shard things. You can consistently hash something and shard it. But that reduces your efficacy in terms of geometric partitioning. How can you geometrically place things so that the things that are closer in geometry are near each other? So this is a trade-off that's always there. Today, what Pinecone does is something closer to sharding, followed by building an index per shard.
So what is so I don't know if you can answer this question, so feel free to push back. But what is the largest cluster of that of a vector database?
It's definitely hundreds of nodes.
Okay.
And we are talking about, like I said, billions of vectors, right? That's yeah.
But it's not kind of the raw material. Let's say, I guess text, images may not so much. So text, if I update the underlying raw material, how easy is it to update the embedding in the database? Let's say I have this billion corpus text thing. I calculate the embeddings, I put them in Pinecone, and then 2 weeks later, maybe 1 million of them got updated. Does it make sense for me to do the embeddings again from scratch for all 1 billion? Or do I just update the embeddings for the 1 million?
By the way, this is one of the unique things about Pinecone is we do incremental indexing.
Okay.
So you can just send us the updated vectors. In fact, we have APIs where you can just send us what has been updated.
Okay.
The hard part is on us to make sure that we don't have to rebuild everything and we can actually incrementally index and so on. That's one of the hard problems of this sort of a database. But for us, you just send the updates. Yeah.
What about so I'm assuming you take care of fault tolerance.
Yes. Yes. Fault tolerance, reliability, recovery, all of this stuff is taken care. It's all the regular parts of a database is taken care of for you.
So this is a fairly young space, right?
It is. It's like I said, it's an emerging category. So it's fairly young space. The concept of vector databases is fairly new, and we're still figuring out how to design this sort of a system. It's a very complex system to build.
And the reason I ask is, how much education do you folks still have to do, or is it mostly the people who already know they need this come to you?
Yeah, there's a lot of people who already know they need this, and they have a good idea of what semantic search or what vector search can do for them, and who come to us often. We do a lot of education as well. But I think today, a lot of people who find us are ones who already know the value of vector search, and what we try to do is to really provide the best platform for them to be successful.
So, I'm assuming you have all of the kind of the so-called boring enterprise features, security, privacy, access control.
Yes. Again, enterprise features, there's like a laundry list of them. We are still very early, I would say, in having the gamut of all enterprise features that typically databases would have. But yes, security, certain limited form of ACLs and so on, we do. Yeah.
Do you think there will be a point where, okay, so part of the vector database is even encrypted?
I'm sure it will, yes.
Yeah. So I noticed that you had a major release recently.
Yeah.
And to my consternation, you guys threw out RocksDB.
Okay.
Because I'm friendly with Druba, I don't know. Yeah. So, but I read the reason why you did it. So, but tell us about this new update of Pinecone, and I guess the main thing that I want to emphasize to our listeners is the update actually doesn't affect the users.
No.
Right. So it's strictly a backend update for performance and scalability, right?
Yeah, so the current release had multiple updates. So we released a new type of graph index. We released something called collections, which allows us to collect the data separately from the index, making it easy for people to do a lot of new use cases with them. We also released something called no downtime vertical scaling, which allows you to just vertically scale the pods without any downtime and so on. The last thing we released, which was like a backend release, purely an infrastructure sort of release, was replacing the underlying storage engine we use for the vector database, which used to be RocksDB. We replaced it with this new storage engine that we're calling Memkey. I think that's
so this is your own storage engine that's not open source, right?
Yes, this is not open source. Yeah. By the way, RocksDB. I know Dhruba as well. RocksDB is a phenomenal piece of software. It's just
and it's used everywhere.
It is. It's you cannot go wrong, I think, to start with RocksDB. Meaning, if you started with RocksDB, I think it's generally a good idea. There was a few reasons that we ended up kind of moving away from it. Some of it also ties to kind of what our code base is written in and what our kind of, for example, our code base is written in Rust now. Majority.
Yeah, I read the post. It seems like you folks actually didn't know Rust when you decided to use it.
Yeah, we did a little bit, but I wouldn't say that we were all experts at Rust.
Yeah.
I had used Rust before. I knew enough about it to kind of know what it's capable of and so on. But I wouldn't say that any of us were an expert at Rust. But because we used Rust and because we did that rewrite and so on, we didn't want to add too many layers on top of Rust in order to really do deep things with. For example, RocksDB is written in C++. There are Rust bindings to it, but there's a lot we need to do if you had to go very, very deep into RocksDB in what we were trying to do. Secondly, RocksDB is designed from a very specific perspective. And we were trying to fit vector search into some of those perspectives just so that we didn't have to rewrite the storage engine. This is a trade-off that you have to sometimes make, which is sometimes you're just trying to use an engine in a way it wasn't quite designed to be used. And at some point, you have to just decide, actually, my use cases are quite different enough that it merits a proper storage engine. That's kind of the place where we came to when we had to do this rewrite, which is we were using RocksDB in ways where we could clearly see that we are losing performance in the way we are using this. There are some trade-offs that RocksDB makes, which makes a lot of sense in the general use case, but for us, that's not the right trade-off to make. Also, making extensive changes to RocksDB would require a real big investment on the C++ side to do a lot of these kind of very core changes on RocksDB side, which it does have good interfaces for, but it requires a lot of effort on our side to actually really adapt it to our use case. But at that point, you're essentially rewriting most of what we wanted to do anyway. So it made a lot of sense for us at that time just bite off the problem of writing the storage engine. And the main reason we hesitated was this is a very fundamental change. Right? Anytime you're writing a storage engine, it's a very fundamental thing that you need to think about. It's only when we landed on a very clean and simple design that I felt very confident that you could actually write correct storage engine kind of code and not it wouldn't be a big risk. That's when we took the decision.
So now we have to lobby Edo to open source the storage engine, huh?
It could happen. I mean, it's not our core competency. Like, it's not necessarily, something that we are core competent on. But meaning, it's not like the core of what Pinecone does, right? I think as long as it's like a competitive advantage and there is something fundamentally, we keep fundamentally pushing innovations in here. I still see it as being proprietary. It'll probably make sense for us to keep it proprietary. At some point of time, it gets commoditized. Any of these things, after a point in time, it'll get commoditized. We can always revisit it there.
So one of the things that actually happens with databases and generally any piece of infrastructure is that sometimes you need to go back and check logs and records for whatever reason, right? So you need some sort of notion of lineage to audit a model, to audit data, to audit why something went down. So what do you folks provide around lineage and reproducibility?
You mean for customer embeddings and stuff like that?
Or you just assume that, okay, so I did a recommendation 6 months ago. I had a recommendation model 6 months ago, and for some reason I want to revisit it, but how do I do that if I don't have lineage for the data, right? So I guess I have to kind of have snapshots and whatever.
Yeah.
So
Yeah. So we provide snapshots. There's a feature we're working on that allows you to export data from the database and so on. There's a lot of things we can do there, but fundamentally we don't tackle the problem of lineage. That's a separate layer. Usually that sits on top of something like this database. Yeah.
So what's on the roadmap for vector databases in general, not just Pinecone? So now we have new things on the horizon, right? So now we have these stable diffusion models, we have transformers. So will the evolution of vector databases around fundamentally kind of align with whatever's happening in the deep learning world, do you think?
Yeah, I think, look, vector databases, we are still very early, but we kind of know where it's at least heading. First of all, most of vector search is focused on essentially static data, right? So you collect all your embeddings.
I mean, it sounds like you have to batch load these embeddings, right?
Exactly. Exactly. Which is not what we do, right? Pinecone doesn't do that. But it's still very, very much R&D, meaning coming up with really good techniques for indexing vector databases, which are fast to update, fast to deal with deletes, and.
But you mean like embeddings that change in a streaming fashion?
Oh yeah. Which is what happens to us. Like customers of ours just send vectors anytime. There's people who are constantly ingesting vectors, constantly updating, deleting, and so on. And they expect their indexes to be fresh, which is what we do. But it's a hard problem to solve, both in terms if you both want latency, QPS, and all that, but at the same time want a reasonable cost. It's a very hard problem to solve. Right? A lot of our R&D efforts are around reducing the cost of such an architecture, and cost is very important because that's the single biggest driver for adopting new technologies and new use cases and so on. Right? So vector search may be extremely powerful, but many companies may not even try those use cases simply because of the cost or of just the cost of trying these things out and so on. While Pinecone has done a lot in reducing the cost here, there's far more we are doing. And this is I think it's a very active area, not just for Pinecone, but I think for vector databases in general. They should really focus on how to make this technology far more affordable and far more cost-friendly in a sense.
And by the way, Ram, for our listeners, the level of performance is very different, I think, than what people are used to. So, for example, when you do a query against a data warehouse, you have certain expectations, but when you query a search engine, your expectations are much more demanding, right?
Yes, much more demanding, and you are far less tolerant of P99s and P95s and so on. So most of our use cases demand 100 millisecond latencies, right? And relatively tight P95s and P99s, and this is across corpuses that are really huge. So if you want 100 millisecond latencies in a corpus that's billions of vectors, you certainly are. It comes down to cost for coming up with really.
Yeah, that's why I was asking. So this index. So it's really, you're not searching the vectors themselves. You're searching the indexes, right?
Yeah. So yeah, you're given a query, right? You're given some query, and you want to find the closest vector or set of vectors in your corpus that are closest to that query. Now, if you think about the naive way of doing this, in SQL, you would just write like a top K, right? You would basically have some distance function. You would say, use this distance function between the query and any data point, and then sort and return for me the top K, right? This in SQL would basically have to go and scan your entire corpus.
Right.
And scanning a billion vector corpus will take you forever, right? What we are trying to do is to make sure that you don't have to scan the whole corpus. The indexing's entire job is to make sure that the amount of data you scan is in a sense proportional to the data required to answer the query. That's a fundamentally hard problem.
And that's something that even in the SQL database world, they spend a lot of energy on index strategies, right? So
they do, but the nice thing about SQL databases is that a lot of this can be done. For example, you will sort by some key.
right.
As you get the data, you kind of know what to do, right? It's only when you start going to geospatial databases that you don't quite know what to do when you get the data. You have to actually have offline processes that somehow try to geometrically collocate data, right? But all those techniques kind of break down miserably once you get to vectors with high dimension. Like geospatial works because it's two-dimensional data or three-dimensional data, right? Once you start getting into 768 or 1024 or 2048 dimensions, none of those spatial partitioning techniques work. You have to come up with completely new ones.
And so then, so the indexes you folks take care of.
Yes.
So given the billion embeddings I send you, you come up with what you perceive to be the optimal indexing.
Exactly. We take care of all that. You just simply ingest data. We provide you an API through which you simply keep ingesting data. You can delete data, you can update it, and so on. Our job is to come up with that scalable index that is fresh to update, make sure that the latest query you run reflects the latest state of the index, and so on.
Wow. And then to do that against kind of, like you said, high dimensional vectors, and to do it in a way where people have gotten spoiled in terms of how fast they want things, right?
And they need it, right? A lot of these are consumer-facing applications. So you can't run like a product recommendation engine and have it run a query against a vector database without expecting it to return in less than 100 milliseconds, right? So those use cases simply demand that low latency.
And there, I'm assuming there's also are there industrial applications as well of vector databases?
You mean enterprise or?
Yeah, well, yeah, like in not consumer facing, more like like a vector database, like a machine to machine almost, a vector database supporting another downstream application, right?
I'm sure there is, but there is definitely like I mean I know like I said, enterprise search is a great example.
Right.
I don't know of any off the top of my head that's a machine to machine use case, but I'm sure there is.
Yeah. And with that, thank you, Ram. We will follow the space closely. So if you were to guess in 2 years from now, do you think this category is more or less somewhat established? Because I guess the other thing that I wonder with some of these specialized databases is at what point does someone decide, okay, so we have enough need to warrant another system, right? So in other words, a lake house is not enough or whatever it is that I'm using.
Yeah.
And I used to use a graph database for some of these things. Now that's not enough either. Yeah. Now I need a third category, right? So at what point do people start saying, yes?
That's a great question. Yeah. By the way, that's already happened. Like this category doesn't exist just because of
marketing,
right? Yeah. It's already the case. People who have been using traditional search engines like Elastic and so on are coming to companies that are doing vector databases like Pinecone, for example, simply because they're not getting what they want out of existing technology. So this category exists for a reason. For a database exists for a reason, and you can't build it on top of existing databases, which is kind of why we had to kind of go build it. I think this will be pretty mature and I think this will be like a pretty mature category in a couple of years, and I wouldn't be surprised at all. What I do think is going to may not be that obvious, but I think strongly holds is you're going to start seeing not just semantic search use cases, not just product recommendations and these sort of things being powered by vector databases. You'll actually see, like I said, security, enterprise search, and like a bunch of these use cases that traditionally used to belong in enterprise search, security, observability, and so on. I think a lot of those you're going to see it like a no-brainer to be powered by such a database. That's what I think will happen in a few years.
Yeah, that's interesting because that whole category where Elasticsearch, Lucene, all those all those systems operate. I mean, those are old systems that run on the JVM, right?
Yeah, yeah, and a lot of those use cases are going to migrate to a technology like this, right?
And
Uh,
also, they haven't been all those technologies have not been refreshed with all these developments in ML.
yes,
Yeah.
yes, yeah. Now, of course, there's a lot of work to be done. So this is I'm speculating what will happen in the next couple of years, but there's a lot of work to be done because some of these old technologies are and use cases are good, which is why customers are using it, right? Keyword search, for example, when it works really well. When it doesn't work, you need something like vector search. But there's a lot of research and a lot of momentum around kind of a way to converge these two ideas so that you can have vector databases power not just the emerging semantic search use cases, but a much broader set of use cases, including what used to be powered by traditional keyword search.
And the vector database space also needs to kind of maybe coalesce around some standard ways of talking to these systems so that people can start building the equivalent, for example, of BI tools, right?
100%. Yes, there's a lot of work to be done there as well.
Yeah. And with that, thank you, Ram.
Thanks so much.